Good morning to everybody. Thanks to the chairperson of this nice workshop. And I'm sure, as Peja has mentioned, that we are advancing. And also, although the first workshop organized by Professor Obradović was excellent, and I think we are on good track to achieve something useful and somehow to relate our, let us say, local science to more international environment. So thanks again to Zoran, and thanks to Peja for nice introduction about the options we could use. Okay, I have already told good morning. Now just hello to old friends as well as new friends. I have seen a lot of young faces here, and I suppose that they will be stimulated somehow to deal with the topics we are addressing. Okay, my talk will be a bit different from Peja's. Actually, it will be more technical, particularly in the second half of the talk, but I'm sure that the first half will be enough clear to everybody, so maybe somebody will be somehow curious to address some of the problems which will be mentioned. Okay, what we are talking about today. Here is the roadmap. First of all, I would like to tell you something which could be considered as a preface, and then something from historical perspective and some introductory note. Actually, the second half will start from here, and it will be, as I have mentioned, more technical than the first part. So if you cannot follow everything, don't worry, that's quite natural. Okay, let's start. So, what we are talking about today, we are actually talking about one of the challenges. You know, this is a story, actually a booklet from National Academy of Engineering in US, and recently they have published 14 key challenges. Let us see what are key challenges according to this document and this institution. Okay, here is copy from the booklet. Front page I have just shown to you. And 14 challenges are addressed here. So you can see the titles. Of course, maybe not so easy to see, so I have rewrite the challenges. And I was free to point out something in red, because that is what we are going to talk today. Actually, besides all other challenges, I think each of these challenges, each one is very important, but I will focus my attention to something which is called secure cyberspace. Why? Look, I'm sure you are aware that there is very strong interaction between our real world and cyberspace. And it is advancing, let us say, every day. And what is interesting, actually, cyberspace becomes more and more rich. We are moving a lot of issues into cyberspace. And maybe this is not somehow good prediction of the future. Tomorrow, you know, we could be mainly in the cyberspace and less in real world, because there are a number of research activities which should provide us not only with three-dimensional effects, but in cyberspace we will be able even to touch something. And then actually you're like in real three-dimensional world. But what is the problem? The problem is that the cyberspace is very, very complex. And although cyberspace provides us with a lot of, let us say, advantages, actually we can face a lot of very, very dangerous issues. And due to that, cybersecurity is one of well-recognized problems which should provide us with, let us say, appropriate framework for moving our activities from real three-dimensional world into cyberspace. Okay, of course, today we are not going to deal with all aspects of cybersecurity, but we are going to address some of them. So this is somehow one typical photo picture what we are talking about. So we are talking about some, of course, digits moving all over us. We cannot touch these digits, but these digits could provide us with an environment where we can enjoy touching each other, although we are miles and miles from each other. Of course, this is future, but very probably very nearby future. And if we are facing such a situation where we are in some very complex space where everything can happen, of course, security is extremely important issue. And if we are talking about cybersecurity, actually, we should point out that there are two additional components. First is cryptology. Second is information security. And finally, if we consider everything as one, let us say, topic, then we are talking about cybersecurity. What is important? Cybersecurity is impossible without cryptology. But cryptology is not enough to obtain cybersecurity. And today's talk is addressed to some issues in cryptology which could be of high interest for information security as well as cybersecurity. Why? Because, as I have mentioned, we must somehow protect ourselves in cyberspace. And of course, if we are going to protect ourselves, that means we should pay some price. And of course, security is not the main functionality. We are not in cyberspace because of security issues. We are in cyberspace in order to have some good functionalities. And if we should protect our visit to cyberspace, it could be very costly. So what is a big challenge? A big challenge, for example, even in cryptology, is to develop techniques which minimize overheads regarding security mechanisms which should be employed in cyberspace in order to achieve our desired goals. And here is abstract of my talk, and I would like to point out just on this left-hand side, and it is written. This is actually what we are going to talk today. First of all, we should identify that an important topic of data science is data security, where data confidentiality appears as a very important issue. And what I have already mentioned, when a heavy employment of encryption is necessary, minimization of the overheads and fit into available constraints regarding implementation are very, very important and require a lot of advances in comparison to what we have now in order to obtain something which is secure and do not enforce high overheads regarding security mechanisms which should be employed in order to achieve desired goals in cybersecurity. So we are talking today about this. But before we start to talk about technical issues, just a little bit of history. So I think a lot of you know, but maybe somebody does not. So I would like to point out to you Enigma. This is German encryption machine which was heavily used in Navy. Why in Navy? You know, it was very important to deal with encryption of messages. You know, if you are in the field, ground field, of course, you can send somebody and to run and deliver messages. If you are in Navy, you know, you cannot order somebody to swim to the next ship and deliver the message. Also, there are submarines. So, due to that, Germans have developed very sophisticated techniques for that time to protect communication between ships and submarines and related issues. Okay, and this was the machine which was used for encryption. It is well known, called Enigma. And of course, on the other side, people in UK, US, Poland, they were trying somehow to break the encryption scheme in order to learn what will happen. Because if you send some message, actually you're sending something which will be clearly effective in nearby future or in future. And if you know the future, you have high benefit. So what was the problem? The problem was, let us break Enigma. And that problem was considering, after all, of two issues. First of all, even it was before Second World War, Polish mathematicians, they have found a way how they can somehow touch that problem of breaking Enigma in mathematical way. What they were needing pairs of so-called plain text and ciphertext. After all, after performing some mathematical operations, when you know these pairs, exhaustive search over a subspace was necessary. Why I'm talking this about? Because it was a big challenge, and that big challenge is now what you have on your desks. That challenge has provided us with computers. The first computer, called Bomb, was designed to break Enigma. So Enigma was stimulation. What we call now cryptology was stimulation for another technological breakthrough for appearance of computers. This first computer was designed by Alan Turing. Maybe you have enjoyed movie Imitation Game. Have you seen Imitation Game? So this is actually story from Imitation Game. Why Imitation Game? Because this first computer was able to, in parallel, imitate a lot of enigmas and perform exhaustive search in order to solve some mathematical problems which were not possible to solve in another way. Okay, later on, new generations of computers have appeared. Please note, this first computer was a computer which had just one program. Program was breaking Enigma. Of course, later on, we were able to enjoy computers which are programmable. And of course, nowadays, we have big data and all these topics regarding data science. So, also I would like to point out another issue, how important cryptology was. And actually, I would like to address establishment of cryptology and information theory. Of course, we know that people were dealing with encryption for centuries. But it was not story about cryptology. It was, let us say, story about art of secret writing. And cryptology is established, has been established relatively recently. Actually, father of cryptology was Claude Shannon, or is Claude Shannon. Claude Shannon has put art of secret writing into mathematical framework and moved from art to science. And what has happened? He has published 2 key papers just after Second World War, because during Second World War he was working on both topics, and he has established information theory on one hand side and cryptology on the other side. Some people believe, I don't know whether it is entirely correct, but maybe a bit correct, whether this paper has appeared by mistake. Because that paper has shown what is the perfect crypto system, somehow unbreakable crypto system for that time. And of course, it is desire of everybody who is in this area to read messages. And if you have perfect system, you cannot read messages. So due to that, some people were telling that maybe that second paper has appeared as a mistake. But after all, these 2 key papers have provided us with background, and that background was expanding, 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 and now we have a huge amount of results relevant for cybersecurity. What is interesting and why I'm pointing out these 2 papers? the first one was related communications, the second one to cryptology. And for almost 50 years, these two tracks were somehow, they were developing independently. This track has provided us with error correcting codes. The other one has provided us with a lot of techniques for what we are calling now cybersecurity. That means techniques for encryption, authentication, digital signatures, and so on and so on. But now I would like to point out to you that recently, again, we are facing crossing of these two tracks which were developing somehow in parallel. And that is somehow a technical part of my talk. What we are talking about? We are talking about, again, joining results from coding theory and traditional cryptology in order to achieve our goal. And as I have mentioned, our goal is to have secure cyberspace, but at the same time to have reduction of the overheads to pay price as low as possible for developing security mechanisms which provide us with high security and at the same time are somehow not expensive in any sense, in sense of implementation cost, in sense of communication cost, in sense of power consumption. And that is very important because as we know, sometimes we are facing with some tiny machines all over cyberspace which have tiny power, and then it is very important to minimize power consumption in order to reduce the cost of employment of these mechanisms. So now I would like to point out to you to two results from coding theory which are of high interest for developing this new generation of advanced cryptographic techniques which provide us with the desired goals, as I have mentioned. So at the same time to be somehow provable secure and to minimize the overall overheads. So there are actually two main classes of noisy channels. Of course, I know everybody knows what is noisy channel. When we communicate from each to other, you know, we are actually using some communication channel. And usually these communication channels are with certain noise, particularly if they are, let us say, wireless communication channels. And actually they are, but same is even if we are on wire, on internet. And on internet, because it is very complex system, we can lose some packets, and it is also, you can model it as a communication channel with noise. So there are two main models of noisy channels. One is so-called channels with additive noise, and the other model are channels with synchronization noise. What is difference? It is extremely important difference. If we are facing channel with additive noise, that means we somehow degrade something which is online, but we know what we are degrading. For example, if we send some bit, or let us say vector or sequence of bits, and we face additive channel, that means each bit will be somehow corrupted, but we know positions of the bits. And the problem with channels with synchronization noise is that we are losing that important information. Channels with synchronization noise destroy our information about positions of the bits which have been sent from transmitter to receiver side. Okay, to be now more precise, for example, this is so-called binary erasure channel. That is very simple model of channel. That means with certain probability, each bit will be correctly transmitted. But some bits which will be corrupted with noise so that we don't know, we cannot decide whether 0 or 1 has been sent. And that is very simple but very important communication channel. The other one is so-called binary symmetric channel. What is difference? In binary symmetric channel, if you send a bit, you will obtain corrupted bit, and you know just probability that 0 will be flipped into 1, or 1 will be flipped into 0, or it will be correctly transmit. But the problem is if we have channels with synchronization errors. Why it is a problem? Okay, look. We are transmitting this vector. But during transmission, bits are subject of deletions. After all, we obtain shrinked vector. That is output of channel with bit deletions. And what is the problem? Deletion of bit is random, and position of deleted bits are unknown. We are losing correspondence between bits in the initial vector and received vector. So this is story about binary channel with random deletion. And this is story about binary channel with insertion. Again, we are sending vector which is subject to random bit insertion. At the receiving side, after the channel, we obtain expanded vector. Again, problem is insertion of bit is random, position of inserted bits are unknown. And now, I would like to point out something which is a bit technical, and it is story about what I have already mentioned. What we are actually facing nowadays, we are facing that sometimes our designs are based on heuristic assumptions, and on the other hand, we need lightweight encryption. So lightweight encryption sometimes is based on heuristic assumptions. So we need enhancement of security, and in order to obtain minimization of the overheads, sometimes we need asymmetric implementation complexity of encryption and decryption. So these are some framework issues. And now I would like to point out to one mathematical problem, which is very important for design of this advanced lightweight cryptographic techniques, which are at the same time provably secure. So there is so-called the LPN problem, learning parity in noise, which is informally solving in its basic incarnation. This is basic. It is problem of informally, problem of solving a system of linear equation when the right-hand side is visible through a binary symmetric channel. And it is well known, actually, that that problem is NP-complete. And you will tell me, okay, if it is complete, what should we talk about furthermore? But it is NP-complete just in the worst case. And of course, this is also a problem of decoding of linear binary block code. And we know there are many, many codes which are easily decodable. So the problem is, this basic incarnation of LPN problem has a potential to provide us with something which can be used for design of cryptographic primitives which are provably secure. But it is just in the worst case. So we should think about generalization. What is natural generalization? Instead of considering something which is visible through additive noise channel, binary symmetric channel, we should consider something which is visible through channel with synchronization errors. And then we are facing this generalized LPN problem, which is a new topic, and there are certain research activities in this topic, but we do not have final results. So then we can use that mathematical background related to the LPN problem to consider two paradigms for security enhancement of cryptographic primitives. One is to employ this paradigm, homophonic encoding, traditional cryptographic processing, and finally degradation of the output through binary symmetric channel, or employ traditional cryptographic processing and simulation of channel with synchronization errors. it seems that this approach could provide us with lower implementation complexity. We can reduce overhead and the costs. So here are some illustrative references regarding what we have up to now achieved. And now, just in 3 minutes, I will summarize the more technical part. So actually, you will see just slides. I will not explain the underlying mathematics because I would like to save a few minutes for the questions. But you will have impression what is the underlying mathematics. It is actually a story about information theoretic and computational complexity security approaches, and how we can perform security evaluation in information theoretic sense. But first of all, this is scheme under security evaluation in this particular story. So we can employ 2 approaches for security evaluation. One is information theoretic, the other is computational complexity. When we apply this approach and achieve some result, that means whatever is power of computers, we cannot do anything within framework we guarantee the security. Computational complexity security evaluation means we can always claim that complexity of certain operation is up to certain limits. And it is good if we know that we cannot reduce complexity of breaking the system below certain level, for example, 2 to 100, that we consider, oh, that's fine. Although we do not have this type of information security. But it is good if we can combine both and achieve some claims in both directions. And here is just slides to illustrate the underlying mathematics. You will see some theorems, formulas, theorems, diagrams telling you, for example, if you have channel with bit insertions, when you have a high insertion of the bits, you reduce, in information theoretic sense, the possibility for breaking the system. And here are some other results. And also we can deal with computational complexity evaluation. We can, for example, establish some theorems. We can later on perform analysis of this information of these theorems and illustrate numerical complexity, or for example number of hypotheses we must face, and we should perform exhaustive search over all these hypotheses. So after all, this is a way how we can achieve provable security and minimization of the overheads required for performing security mechanisms in cyberspace. Actually, I have already concluded, and thank you very much for your attention.
Thank you, Misha, for your talk. Now we have, let's see, we have 5 more minutes for questions.
Ask anything, you know. Any question is good question. And maybe you will take something which would be interesting hint for your further research activities.
I can just
yes,
ask the first question. What stage of development is your system? I mean, is it already a system, a prototype, something?
Okay. Actually, usually the end story of my activities is paper, sometimes patent. Actually, some of these results have been submitted for patents relatively recently, maybe 3 months ago. So after all, maybe somebody will have interest to use this, let us say, intellectual property. And I would like to use this opportunity to tell you something else which could be very interesting. You know, I have a colleague, and when he was PhD student, he has written a paper with his advisor from Carnegie Mellon University, and they have submitted a patent. And that was all. About 15 or even more years, suddenly it appears that Marvell Corporation used that patent, of course, without any permission. And then it was a case in US, and then, it was, the case has started in year 2009, I think, and finished on February 17 this year. I know February 7 because it is birthday of my son, and the news has appeared at the same date. So the question for you is, what do you think, what was compensation for illegal use of that patent? Somebody maybe has seen the link? You know? Okay, the court decision was $1.15 billion. And after all, on February 17, it was settlement for $750, of course, million. Just a little bit reduced. Is it good amount? What do you think, Peja? Pretty good, okay. So if there is no more questions, thank you very much again for your attention.